Now, in the second part of this tutorial, I will be setting up my study. So my part is ready. The axis has been set up. I will now assign a particular material to it. Now, in this case, as I already explained, my material is AISI 1020 steel, but you need to assign the material according to the to your number, and therefore each student will have a different choice here. So I will go on and I'll choose AISI 1020 steel. I'll make sure that all the values are correct, and then I'll just click on apply and then close. So now you can see here after the part name, you've got the name of the actual of the material written as well. It will be a good idea to actually save the file at this stage, because otherwise your progress may not be saved. So I will call it as Fall 2025 instructor. So I'll just call it as instructor version to differentiate it from your copies. So that's now the file, and it has been saved. Next step is to assign the boundary condition. So I'll choose this particular end, yeah, from the end of the origin, at the origin. So for the boundary condition, and I will right click on this and click on fixed geometry. Now you can either constrain the edge or you can constrain the entire face. In this case, I will constrain both the edge and the face. Now, in reality, this may not be the case, because you may only have the edges constraint at the edge, but the equation that we are using, the equation in the background that we are using, the TR over J formula over here, for the derivation, we are assuming a perfectly fixed condition on one of the ends of the shaft, because we are saying that the torque is same throughout the shaft on the free end on which we are applying, but the other end is fully constrained. So to represent that full constraint situation, you apply this boundary condition. Later on, if you want to check and compare the results, you can actually just constrain the edge, and what you'll find out is that the stresses actually drop from the value of the stresses that you get from that formula, at least on the far end of the shaft. So that will be there. So that is the one boundary condition there. But also remember that implicit in that formula that we have derived is the fact that this shaft is not under, like acting like a cantilever. So this cannot bend downwards over here. So this shaft is going to remain perfectly straight. So we also need to apply that boundary condition on the shaft. So that is a kind of a bearing. You can assume that this shaft is in a bearing. So because it is not able to bend downwards while it can still rotate about this axis. So that's what we are going to do by creating a roller slider fixture. So if I just select this top surface, so that will basically represent that this shaft can actually rotate, but it cannot bend downward. So it's preventing the downward rotation, downward motion. So with these two boundary conditions, now our boundary condition setup is complete. Next step is to actually apply the external load. In this case, the load is in the form of a torque, which I can apply on this face. So the entire face, the value of the torque remains same. So I select the face on which I need to apply the torque. I also select the reference axis. So I have to be careful not to select the other surfaces, and I just go on and on here in this pink box, I select this x-axis as the reference. Now you can see here the direction of the torque, which is going to remain same on this face, and the value in my case is 360 Newton meter. Keep this in mind that this unit is already in Newton meter, so I don't need to convert this into Newton millimeter at this stage. This is per item, meaning that it is for this entire face. So that's it, and I will click on OK. And now the torque has been applied as well, and you can see this. So with this, my basic setup of the model, that is the material, boundary condition, and the torque setup is complete. And now I can proceed to the meshing phase. In this case, we will create a refined mesh based on the blended curvature-based mesh technique. You can also use the standard mesh technique. It's not going to create a major difference. But I think in my case, I'll prefer using the blended curvature-based mesh simply because it's a circular part, and so it will all be meshed with the same sort of mesh. When I select this option, and I'm using a high-quality mesh over here, so that's already selected. I'm not going to do a convergence study. There will be some stress concentration on this fixed edge, which will be fully captured because of this fine mesh. We will look into that edge later, but first we will analyze the quantities on this edge because this is where the equation is directly comparable with our simulation results. So I'll click on OK, and now it is going to mesh the part. So you can see here it is a very fine mesh, and probably a bit of overkill for simple part, but I just want the results to be as close to the theoretical equation as possible. So with this option now selected, my meshing setup is complete. I can actually now just simply run the study to get our first set of results. So it will take a few seconds, and now the results have been produced. And you can see here the part looks a little bit, enlarged on this end. This is because of the scale factor. You can either double click on this to correct the scale factor to true scale factor, and you can set the units to megapascal. And in the option, you can show maximum and minimum as well. And I'll go for a floating point representation. And now you can see here. Now, the quantity that you're seeing over here is basically von Mises stress, and you can see here that the stress is almost zero in the center and it is maximum on the top. However, this is not the quantity that you are getting from your theoretical equation. And in fact, we have not yet covered the definition of von Mises stresses in our hand calculations. So I will reserve this discussion for later, that what von Mises stresses is, once I show you the formula in a few weeks. But right now, I'm going to basically plot the value of shear stress tau. And in this case, the shear stress value is basically, as I explained, in the r and theta coordinate system. So or if I call it the angle of twist as phi, so I'll call it as r and phi coordinate system. So I will basically use that here so that it is clear that this is basically tau r phi. Okay, and then what I will do is I will, because in my FE analysis, my answers are the model is set up in X, Y, and Z coordinate system. I will actually plot the value of the stresses, the shear stresses in that coordinate system. So if I go into the defined stress plot, okay, I can now actually go into the XY coordinate system over here. So this is shear stress in basically the Y direction. So the first subscript is indicating is basically indicating the direction of the area normal, that is the YZ plane will have the area normal along the x-axis. So that's the area normal, and it will be along the y-axis on that face. So it will be going upward like this. So that's the shear stress. Now, if I select the units as megapascals, and then I select on true scale, and then in the options, I show maximum and minimum. And here I'm using floating. So with all that option set up, I can now see the value of the shear stress. And what you see here is that your shear stress values are now actually in a narrow band, and you can see that the maximum is around 68.4 megapascal, but it's no longer constant. You can see here is a minus over here, which is minus 68.5, and there is a maximum over here, which is plus 68.4. Okay, and this number over here actually compares readily with this number. However, but we can see here that there is also a negative value here. What this is, and the reason this is happening is because of the coordinate system. And so basically at each location along this shaft, the value of stress is different. And I can actually use the plot tool to probe these values along this entire edge. So if I click on selected entities and then I click on this edge, I will be able to see the value along this entire edge. And you can see that the value is changing. I can actually plot this value on a graph over here. And you can see here that the value is basically changing from a value of around minus 55 and goes up to a value of plus 55 over here. So you can see that this value is not actually constant. And that value of 68, which you are saying, is actually not being seen on this entire edge. Rather, it is being seen on the constrained edge of the sorry, not the constrained edge, but actually uh, here. Yeah, so it's on the constrained edge of the shaft somewhere around this location. Okay, so if on the other hand I choose this constrained edge and I just remove the first option and I update this plot, now what you will be able to see is that I actually get the values which are here varying from plus 68 in the middle of the shaft over here, and downward is the minus 68. And again, along this length, the values are changing. Now, this is not something that you've seen in your hand calculations because of the limitation of the equation itself and because of the fact that it is in r theta coordinate system. So what we are going to do is we are going to now take these numbers out and do a bit of processing on them using a theoretical formula. And then later on, I will show you how you can actually directly do this within SolidWorks as well. So I'm going to now export this data set into Excel. So I've just selected copy from here. So this will copy this set of data along with the node numbers. And I'm opening a blank worksheet. I'll just simply paste my values over here. And the Excel SolidWorks does not in that by default input the quantity name, so make sure you don't forget that. So this is tau xy, right? So this is the quantity that you're plotting, tau xy. So this column gives you the actual value, this column gives you the number of the node, and this column x, y, and z gives the actual physical location of the each of those nodes. Now, for our purposes, the value of x, y, and z is not that important. We are just simply going to compare them, but we just want to make sure that it is consistently plotted for all the cases that we are going to to examine right now. Now, once I've got the value of tau xy, I will also plot the value of tau xz, which is the second shear stress on this. So basically, I can go into stress plot, I can go into xz. So again, remember, the first subscript indicates the direction of the area normal, which is along the x-axis, meaning it's on the yz plane. And the z direction is basically the direction of the stress. So I will again plot this on true scale. And again, I'll get the maximum and the minimum over here and do the floating point representation. And now I plot it. And now if you can see here, what you will be able to see that the stress values, the location is exactly opposite to that of the one. So originally in the previous case, it was basically this direct the locations were maximum were here and here. Now it's on the other edges where it is maximum. So this is a consequence of the coordinate systems. So basically now I will go and I will again use the plot tool. I will again probe these values and I will now click the value over here on selected entities on the edge which is constrained, and I will basically be able to get the number output here. Now I think in the units I forgot to choose megapascals, so I will edit this graph before exporting this value. So I'll go into edit definition and here I will choose the number in megapascal. I need to make sure that the units are same for both cases so that when we are adding them up it does not cause a problem. So this is 68.317 again, which is the number over here and here. So now again I will go into the probe tool. I will select this edge and I will, sorry, I first need to say on selected entities, then select this edge, then update this, and now you can see here the values are changing, and this is the graph actually looks reverse of the previous graph, so it is almost zero over here, goes to the negative maxima and goes to the positive maxima uh, at around this location. So with that, I can now simply copy the data using the copy to clipboard option, and I can now go to my Excel sheet, which I have over here. And in this Excel sheet, I will actually copy all of this data in the next column. So now we have got tau. This value is tau x z. Okay, so this is the tau xy and this is tau xz. So these are the two columns that I am interested in right now, and you can see they are for exactly the same nodes. So this is something we have to ensure. So because we don't want to be adding data from the different nodes, so I will just turn this into bold and highlight this column so you can see which column I will be using for my computation. Now I will basically convert this into tau r theta using the formula over here. So basically, all we are doing is we're saying that this is tau xz, this is tau xy, and then we are going to uh, use the transformation using the Pythagoras theorem, and I'm going to use this value over there. So this is the formula, square root of tau xy squared plus tau xz squared. So I will call this as now tau r phi, okay, from my equation, and this is going to be equal to square root of the tau xy, and we take the square of this, okay, and plus the square of tau xz, and then the whole square root. And now we get the final value over here. You can see that all at this location, this is 68 and this is almost 0, and the net result is 68. And we can copy this formula over for all of the other locations, and you will see that the value is almost constant around 68. There are a few bit of variation, but that is expected because in the case of the finite element analysis, if you look closely, these are this is the edge location. So the contour is not perfectly circular for our element, so there will be some small differences in terms of the radial location, and that difference in the radial location for this edge based on the mesh size that we are chosen, it gives rise to these small variations in the value that we are calculating. So this is the value from FEA for our um, so okay, and for the hand calculation we have already seen that the number is given over here, right, in the values that we calculated earlier. Yeah, so this was basically 67.9 megapascal. So I will call it as hand calc, and this was also tau, and this number is 67.9 megapascal. Obviously, this number is going to remain same throughout. So this is also in the units of megapascal, and this is also in the units of megapascals. So if you want, you can now actually compare these and get the error, or you can see the difference. And the difference between the hand calculated percentage difference between the two is small, you can see. So I will use basically my hand calculated, minus my FEA, and I will use my hand calculator as the reference right now. Again, whether you use FEA as the reference or the hand calculated as the reference, it depends on you. But I'm using the hand calculated as the reference value because I'm comparing against the formula. Okay, so this is 0.0081, which in terms of percentage is actually less than 1%. So it's 0.8% that you are getting, right? So this is the difference between the two values. So it is pretty close to the value. Actually, in most other locations, the difference is even smaller, right? So you can see here that the difference is reduced to 0.1%, 0.1%, and most of the other locations, the difference is actually smaller. So this is a comparison between the theory and FEA as far as the maximum shear stress is concerned. We can now proceed to other part of the analysis where we are going to calculate the angle of twist. Now, in SolidWorks, you cannot directly plot the angle of twist. In other softwares, you can do that, but in SolidWorks, you have to actually use the displacement to calculate the value of the angle of twist. And in this case, the angle of twist will be given as the resultant displacement, which is UR over here, divided by this radial distance. So that will give you the tan inverse of this will give you the angle of the twist. So the SolidWorks will be able to plot for you UY and UZ. So you'll take those two numbers, you'll plug it into this equation to get the value of the resultant. So this is something now that I will be doing very quickly. Let me close this. So now we are going to calculate the angle of twist. But keep this in mind, for angle of twist, we cannot do that on the constrained edge because the constrained edge will have a zero displacement. That's why the edge is constrained. So we'll have to go to the free edge on which we are actually applying the load. And this is the furthest away. So this is for where the length is L. So this is where we are going to plot the displacement. You can directly read the displacement from the resultant displacement option over here as well, but I will avoid that because this also has the third displacement component UX. So for the purpose of comparison with the hand calculated values, I would rather calculate it myself by using the UX and UY. So I will take basically y and uz, not ux. So uy and uz, because the assumption in our hand calculation equation is that the shaft is not expanding in the x direction. So basically, I will now take uy here, and the true scale. I will go into again show minimum maximum and also floating, and I have chosen millimeter as the units. And now you can see here that these are the maximum and minimum locations for the displacement at the free edge. And again, you can plot this for the entire edge. Before I do that, I will also so I'll quickly go on to the probe tools on selected edge. This time I'm choosing the free edge, and I will click on update, and then I can actually show you the variation of the displacement. It looks very similar to our tau xy graph. I will copy this data over, and on the free edge, I will now use this value over here. So let me copy this over, and now you can see. Now keep this in mind, these node locations are different from these node locations because this is on the free edge and the other one is constrained edge. If you want to remember this, you can write this as free edge, and you can say here constrained edge, so you can remember where you obtain the values. So this one is now UY in millimeters. So that's UY. Okay. And after that, I will now quickly calculate the value of UX. So I will again click results, define displacement plot, and I will go and I will plot UZ true scale. Okay, and plotting. Okay, and now you can see here it's 0.527, but so it's the value is almost same, but the location of the max and min is different, and you can actually now use probe tool again on the selected edge, which is at the free edge, update this, and now if you see here, the distribution looks very similar in shape to the shear strain, although shear stress values, although the actual numbers will be, of course, not same because this is the displacement and that was shear stress, but the shape of the curve will look very similar. So I will again now click on copy to clipboard, and this data will now be outputted. So I will again Control V, paste this data over here, and this is also my free edge. This the quantity that I'm plotting now is UZ. Okay, so this is UZ, and I will just simply highlight this so you see this clearly. And you can delete these other numbers if you want, but if you don't want to delete, it's also okay. It's up to you. Now I will calculate from my FEA the value of UR, which is the resultant, according to this formula over here. So again, I will basically it is equal to square root of the UY squared plus close plus UZ squared and close this so I get this value. I can copy over this formula and I will get my U resultant for all of these nodes, right? And I can easily change this to three decimal places for ease of visualization. Okay, and I can now calculate the angle of twist. Okay, so angle of twist, which is phi in radians, is going to be this UR divided by your radius. Okay, and in my case, the radius is 15. In your case, you have to use whatever it is, but then you have to take the tan inverse of this. So A tan of this number, which is UR divided by radius. So that is going to give us the angle of twist in radians. So you can see here this number is actually very close to the value that we calculated. So this is the formula, and the value that we calculated from our hand calculations was 0.03504 radians, which in degrees was 2.008. So I will actually calculate now this in degrees as well. So degrees. So you can see here that this is 2.001, and you can actually also use hand calc, and you can, okay, and this one is 2.008, yeah, approximately, and that's going to be same based on the theoretical equation. And now you can actually calculate the percentage difference. Okay, so you can do that in the very same way as the previous case. So based on the theoretical minus the FEA divided by the theoretical. And so you can see here that this is percentage error is actually very small. So it's around 0.4%, actually 0.397. And if you see, it will even reduce on other nodes, even below that. So the maximum is around 0.397. And this difference, as I've already explained, is because of the slight differences in the nodal locations along the edge, which are not perfectly. You can see here this point is at -15, whereas these points are slightly different locations. So, uh, so that's what we need to do. Make sure you plot these curves that you have taken. You can take the screenshots or you can export directly using SolidWorks. I will not go through how to take those. I expect you to be able to do that. And then you will have to answer these and confirm some of these answers over here, give the percentage errors as well. You will also need to then calculate the factor of safety. And now how you are going to calculate the factor of safety to calculate the, just like we did this for our FEA analysis. For the factor of safety, you'll take the basically the shear stress and compare that with the shear strength of the material. Now that is slightly tricky because do you actually have the shear strength or not? Let's quickly look into the material data card. And if you see this, the material data card, you can see here that this gives you the tensile strength, but it does not give you the material's shear strength in this data card. So what I would recommend is that now, based on what we covered in the lecture section about the different types of failure criteria, like the Tresca criteria, and also considering the type of the material, you actually first get a value of the shear strength for your material, and then use that to actually calculate the factor of safety using the shear stress criteria. And also, once you have done that, you can also compare it with the maximum angle of twist in your particular case. Okay. And for the FEA, just use the maximum largest value, and similarly for your hand calculations, use the value that you have from the equation, which will of course remain same throughout the edge of the shaft. Now, in terms of the further comparison and discussion, what I want you to do is I'm saying if your shaft achieves the desired factor of safety and allowable angle of twist based on this analysis, then you should suggest some appropriate design changes so the mass can be reduced by at least 25%. So, without changing the length, let me add that. So, I don't want you to change the length. So, I, I want you to keep the length same, but I want you to think about, for example, the changing the diameter of the shaft or changing, some other parameters to see if you can achieve the um, you can have the same desirable factor of safety and angle of twist while reducing the mass by 25%. So you basically need to think about mass in terms of volume into density, and then the volume will be area of cross section into the length. And I'm saying keep the length same, just change the shaft. So maybe you can make it hollow or something like that. Secondly, if your shaft does not achieve, because obviously different students will have different scenarios depending on their material, torque, and everything. So if your shaft does not achieve the desired factor of safety or the allowable angle of twist, then suggest appropriate changes, noting that you do not want the mass of the shaft to increase substantially. So think about, for example, changing the material, and you can do this and then reflect on this here. You can do this through FEA analysis or through hand calculation. It is your choice. But whatever you do, make sure you show either the calculations if you do by hand calculation or the results in the form of the actual FE analysis if you choose that path. So please make sure you complete this task. I hope everything will be clear, but obviously I can explain to you if you have any more questions in the class. Thank you very much. This is it from my side. Yeah, just one more thing. If you want to quickly, what I'll do is I'll just copy this study and I'll give it a new name and I'll just say only edge constraint. So I'll demonstrate to you some of the changes that will happen if you are going to change the boundary conditions, right? This is not part of your actual lab. You don't have to do this, but you can. I will demonstrate it to you just in case, so you understand that the differences. So in this particular case, if I now change this boundary condition, edit definition, and here I don't, let's say, constrain the face, and I just constrain the edge. What you will happen now, I will of course have to rerun the analysis because my results file will be invalidated. So once I rerun the analysis, so you can see here the max value of the one mises has changed, and because we were comparing the XY, you can see here suddenly the effect of stress concentration has become significant because now what you're doing is you're letting this rotate, but only the edge is constrained. So that's a much more severe boundary condition as compared to making the whole edge as fully constrained. Okay, because the stress concentration is now only around this edge. So this should also tell you something about, if in a real situation, the importance of making sure that when you're constraining a particular part, you constrain it in such a way that the constraint is being distributed on the face rather than just on an edge. Okay, that's one thing that I wanted to highlight. The stresses, by the way, on the free edges are not going to change significantly because of this, because they are going to remain almost the same as before, the actual values. The graph will look different in terms of the colors because of the fact that now your graph is being, the range is being clouded because of the change of the highest and lowest stresses. Another thing that you can do, for example, so remember, if I again copy this, the original one, and this time I will call it as fully fixed, but I'll just call it as no bearing. So basically, I'm removing the sliding, going to remove the slider constraint. So I'm going to just simply suppress this. And now if I rerun my analysis, what you will see, it is still running, right? And immediately you can see here that again the distribution has changed, and this time this is actually also bending downward slightly. And now the stresses not only on the extreme edge, rather on the free edge are also going to change. Okay, so if I just simply plot, probe the values, right, on the edge, and I show you this number, what you'll see is that this number has slightly changed. But what will actually make it more obvious to you will be if you plot the x-axis stress. Because ideally, my x-axis stress should be 0 because I'm not applying any load along the x-axis. Yeah. And I'm not actually causing it to bend as well. So in this particular case, you can see here there is some x-axis stress. I need to just simply change the chart option so it's more easier to read. So you can see it's around 23 megapascals of the stress on the fixed edge, while, sorry, let me zoom this out. Yeah, so it's on here. So you've got the maximum and minimum over here of the x-axis stresses. Okay. And on this edge, if I probe, you can see that the value, if I plot it, is actually going to be quite small, but it's, in this narrow range. But on the fixed edge, right, which is here, because that is the free edge, so that does not matter. But here you can see there is a significant stress. So if I just now plot this one, sorry, wrong edge, selected, need to delete this, and now select this edge, update it, plot it. And now you can see here that you've got a significant amount of extras. You can compare this very quickly with the correct model that was over here, right? And here, if I now plot x-axis stresses and in megapascals, true scale, showing both maximum minimum, floating. Now you can see here that the maximum stresses at this constrained edge are also very, very small. Can you see that? Yeah, it's only 1.827 as compared to 23 megapascal. So that's also one way you can validate your analysis setup, because in reality you won't have always hand calculations to make sure that your analysis setup is valid. So how do you calculate is you try to figure out which components need to be zero, which components should be nearly zero. So you can see here now that it's only around 0.15 megapascal that it goes on that edge, instead of the 23 megapascal that I was seeing here when I was applying the bearing loading. So these are some of the things which you don't have to do, but again, if you want, you can do them to understand the different ways in which the model can behave. Um, so I hope this will be insightful for you. So thank you very much, and I hope to see a good report being produced and submitted by the due date.